chain rules for functions of several variables, very similar to the study of chain rules from Calculus 1. Here we apply chain rules, the same concept, but expanded upon a function of more than one variable that it depends on. Typically in Calculus 1, you have a function f that depends only on x. Here, a function could depend on x and y, but then even within the numeric chain, x can depend on several other functions or variables, and y can depend on other variables as well. First, the chain rule for the one independent variable. This, my friends, is identical in the hierarchy of things to the chain rule from Calculus 1. Let w be a function of two variables, w equal to f of x and y, where f is said to be differentiable in x and y, and x is a function itself and y is a function. X is the function g of t, and y depends on t with respect to h. So where also g and h are differentiable functions of t, then you can write w being differentiable as dw over dt is the partial of w with respect to x times dx over dt plus the partial of w with respect to y times dy over dt. Let's consider some problems making use of that. Here it says find dw over dt, just the above theorem, using the appropriate chain rule. Evaluate dw over dt at the given value of t. So we're looking for dw over dt, which is set to be the partial of w with respect to x times dx over dt plus the partial of w with respect to y times dy over dt. So this gives us this partial of w with respect to x is equal to 1/2 times x squared plus y squared to the negative 1/2 times the derivative of the inside with respect to x, which is 2x. So you can just write that as x all over the square root of x squared plus y squared. So we'll plug that in here. This is x all over the square root of x squared plus y squared times the derivative dx over dt. Well, that's just the derivative of the cosine, so here we get negative sine t. Plus now the derivative of w with respect to y, which x and y for w are symmetric, so this is y over the square root of x squared plus y squared times dy dt, which is just times e to the t. We simplify that, so dw over dt is equal to, here it says to evaluate dw dt at the given value of t. So that begs to reason you want to write this derivative function with respect to t. So x would have to be replaced with cosine t and y replaced with e to the t. So here we have x times negative sine t. This is negative cosine t sine t all over the square root of x squared, which is cosine squared t, plus y to the second x squared, which is cosine squared t, plus y to the second, that's e to the 2t, plus y, which is e to the t, times e to the t, so we get e to the 2t there, and that's all over the square root of cosine squared t plus e to the 2t. Now it says evaluate dw over dt at t equal to 0. So if we do that, we have negative cosine 0 times sine of 0, which is just 0, plus e to the 0 all over the square root of cosine of 0, which is 1, plus e to the 0, which is 1. Right? So all we have left is 1 over the square root of 2. In exercise 5 to 10, find dw of dt by part A by using the appropriate chain rule, and then part B by converting w to a function of t before differentiating. So basically they're saying part A, use the formula above, and then part B, convert back to calculus 1. Let's see. So part A, we're looking for dw over dt. This is the partial of w with respect to x times dx over dt plus a partial of w with respect to y times dy over dt plus the partial of w with respect to z times dz over dt. So dw over dt is equal to the partial of w with respect to x. So this is y squared plus 2xz times dx over dt, which is just 2t, plus the partial of w with respect to y. So that becomes 2xy plus z squared times dy over dt, that's just 2, plus the partial of w with respect to z, so this is 2xz plus 2yz times dz over dt, that's 0. So now what you need to do is to replace all the x, y, and z's with their respective representations. So this dw over dt is equal to the y squared is 4t squared plus 2 times xz. 2 times, well, x is t squared and z is 2, so that's 4t squared times 2t plus 2 times xy, and x is here, this is y, so that's 2 times 2 is 4 t to the third plus z squared, that's 4 times 2, and it's just 0 there. So now we simplify, we get 8 times 2 is 16t to the third plus 4 times 2 is 8 t to the third plus 8. So dw over dt is equal to 24 t to the third plus 8. Part B says take w and write it as a function of t. So this is xy squared, so the x is t squared, and then the y squared, that's going to be 4t squared, plus x squared z, that's 2t to the fourth, plus y z squared. Y is 2t times z squared, that's 4, so that's 8t. We can simplify that. So this is 4t to the fourth plus 2t to the fourth plus 8t. Simplify that again, we get 6t to the fourth plus 8t. And so Calculus 1 tells us that this is the dw over dt. Just take the derivative directly, and that gives us 24t to the third plus 8. You get the same thing. So you know you're on the right track when you get the same thing, and you're supposed to get the same thing. What about the chain rule for two independent variables? So the same premise, let w be a function of x and y. But now, and here f is differentiable in x and y. But now x doesn't depend on one variable, x depends on two variables. So x depends on s and t, and y also depends on s and t in different formats. So we have the function g and the function h. Let all the partial derivatives, the first partial derivatives, exist. That is, let the partial derivatives be continuous. And so then you want to find the partial of w with respect to s, and then the partial of w with respect to t. If they exist, then they're calculated in this fashion. So it says find the partial of w with respect to s. Well, this is said to be the partial of w with respect to x times the partial of x with respect to s plus the partial of w, yes, with respect to y, times the partial of y with respect to s. If there was a z, this would be plus the partial of w with respect to z times the partial of z with respect to s. If there's a u, then the partial of u with respect, the partial of w with respect to u times the partial of u with respect to s, and you just keep on going. It's a chain. So, yes, the partial of w with respect to x is 2x, and then the partial of x with respect to s is 1, plus the partial of w with respect to y is 2y, times the partial of y with respect to s, that's 1. So that gives us 2x plus 2y. Replace the x and y with their respective values. So dw over ds is equal to 2 times s plus t plus 2 times y, and that's s minus t. So that gives us 2s plus 2t plus 2s minus 2t. So that just gives us 4s. And if s is 1, then we just get 4. So now the partial of w with respect to t is the partial of w with respect to x times the partial of x with respect to t plus the partial of w with respect to y times the partial of y with respect to t. So the partial of w with respect to x and the partial of w with respect to y, they stay the same, right? 2x and 2y. So this is 2x times the partial of x with respect to t, that's 1, plus the partial of w with respect to y, that's 2y, times the partial of y with respect to t, that's negative 1. This partial of w with respect to t is 2 times x, but x is s plus t. This is minus 2 times y, and y is s minus t. We simplify that, so this is 2s plus 2t minus 2s plus 2t. So the s's cancel, so the partial of w with respect to t is equal to 4t, and t is evaluated at 0. And we get 0. Here, find the partial of w for exercise 17. Find the partial of w with respect to s and the partial of w with respect to t by using the appropriate chain rule, and then part B by converting w to a function of s and t before differentiating. So part A, find the partial of w with respect to s. This is the partial of w with respect to x times the partial of x with respect to s plus the partial of w with respect to y times the partial of y with respect to s plus, yes, the partial of w with respect to z times the partial of z with respect to s. So the partial of w with respect to s, this is equal to the partial of w with respect to x, that's y times z, times the partial of x with respect to s, that's times 1, plus the partial of w with respect to y, this is xz, times the partial of y with respect to s, that's 1, plus the partial of w with respect to z, that's times xy, times the partial of z with respect to s, t squared. Now you write everything in terms of s and t. So the y is s minus t, and the z is s t squared, plus the x is s plus t, and times z, and z is s t squared, plus x times y, just the difference of two squares, that just gives us s squared minus t squared times t squared. We simplify that, so we get the partial of w with respect to s, and this is s squared t squared minus s t to the third plus s squared t squared plus s t to the third plus s squared t squared minus t to the fourth. Let's get the terms that are alike together. So s squared t squared, there's one there. Looks like there's one there and one there, so that's 3 s squared t squared. And then what about the st cubed? That's minus and that's plus, so they cancel out. And then we have left a minus t to the fourth. And so it doesn't matter how you write it. if you wrote that as t squared times 3s squared minus t to the second. Now the second thing they want us to do with that is to find the partial of w with respect to t. This is the partial of w with respect to x times the partial of x with respect to t plus the partial of w with respect to y times the partial of y with respect to t plus the partial of w with respect to z times the partial of z with respect to t. Okay. This partial of w with respect to t, the partial of w with respect to x, it's going to be standard here. It's going to be yz times the partial of x with respect to t. That's 1. Plus the partial of w with respect to y, xz, right? There it is there. Times the partial of y with respect to t, -1. Plus the partial of w with respect to z, xy. Times the partial of, get out of there, times the partial of z with respect to t, partial of z with respect to t, that's 2st. Hey, I know a st. Town Creek. Very good, brother. So the partial of w with respect to t, Mr. St, I should say. So we have the yz, which should follow from here. That's the same expression. So that was s minus t times st squared. Then it's a minus instead of a plus from the previous one. That was the plus sign there, but the xz's were the same. So that was s plus t times st squared. Plus x times y. Again, that was the difference of two squares, s squared minus t squared. And this is times 2 times s times t. Now let's simplify all of that. We have the partial of w with respect to t, and this is s squared minus s t to the third minus s squared t squared minus st to the third plus 2 times s to the third times t minus 2s t to the third. The partial of w with respect to t. Let's see what we have. We have that s squared s squared t squared should have been, and this is st to the third, s squared t squared. S squared t squared. Now notice here that s squared t squared we cancel out with this term there, and we have an s, that is an s, t to the third, and then it's minus, and this is a minus st to the third, so they're like terms. And then we have this 2s cubed t, let's write that first, 2s cubed t, then minus these two guys here, 2 times s t to the third minus this 2s t to the third, which is a like term. So we can write this as 2s cubed t minus 4s t to the third. We can write that as the partial of w with respect to t. Factor out a 2s and a t. That leaves us with s squared minus 2t squared. All right, so now let's see. Part B said to do what? Part B says by converting w to a function of s and t beforehand and then differentiating. All right. So part B, w is said to be x times y times z, right? So we're going to replace the x with s plus t, replace the y with s minus t, and replace the z with st squared. So this is x plus t times s minus t times s t squared. Let's simplify that. This is s squared minus t squared times s t squared. And so w is s to the third t squared minus s times t to the fourth. Now we take the partial, well, you can just find, if you will, dw over dt, but anyway, the partial of w with respect to s. Do you understand it now? Why we're looking for the partial of w with respect to s, even up in before with those formulas. It's obvious to see it when you convert it back to calculus 1. So anyway, this is 3s. What kind of s is that? 3s squared t squared minus t to the fourth. Okay. And you can write that as, you factor out a t squared, then that leaves us with a 3s squared minus t squared. Is that what we got before? Yes. T squared 3s squared minus t squared. What about the partial of w with respect to t? Looking at this guy right here. So the partial of w with respect to t, so that's 2s to the third t minus 4s times t to the third. What's common there is a 2s and a t that we factor out. We have left s squared minus 2t squared. I believe that's what we got here. Good deal. So you know that you did everything correctly. So now the last emphasis of this section is the chain rule here applied to implicit differentiation. We're going to use the formulas here that's given to find dy over dx. The function that's given is said to be capital F of xy equal to 0. If it's not equal to 0, you subtract everything, get everything on one side, and then it is equal to 0. We call that function the capital F function. And so the dy over dx is simply equal to negative the partial of f with respect to x divided by the partial of f with respect to y. And the way I keep that in my head is I just match those terms there together. And the same thing here, right? The z's kind of go together. You have a negative sign there. Typically, I do prove this, but if you accept these formulas, then we can just go right at it and show how we can find the implicit differentiation using the chain rule. So what we're going to do is find first here the partial of f with respect to x. So this is going to be 2x minus y minus 1. Then the partial of f with respect to y. Take the derivative of this capital F function with respect to y. So this is negative x plus 2y plus 1. And so dy over dx is said to be negative capital F sub x, evaluated at x, y, you can get formal, over the capital F function. Here's the partial derivative of f with respect to y, evaluated at the point x, y. So this is negative. We put this f sub x first. This is 2x minus y minus 1 all over negative x plus 2y plus 1. And if you run that negative downstairs, this is 2x minus y minus 1 all over x minus 2y minus 1. What about this one? Here it says differentiate implicitly to find the first partial derivatives of z. So we need a few things. You need the partial of f with respect to x. So this is the natural log of y. You need the partial of f with respect to y. And this is x times 1 over y, or x over y plus, take this partial with respect to y, that's 2yz. And then we need the partial of f with respect to z, and that is y squared plus 2z. So the partial of z with respect to x is what you need. It's a negative, and this is capital F sub x. It's going to match this guy at the point x, y, z all over capital F sub z at the point x, y, z. And they don't give us a point, but we still represent it. So this is negative out front. F sub x, that's the natural log of y, and this is all over f sub z, and that's y squared plus 2z. About the partial of z with respect to y. This is negative f sub y. I'll just use my shorthand over f sub z. So the negative out front, f sub y, we found that here. That's x over y plus 2yz. This is all over f sub z, and this is y squared plus 2z. Forgot that negative in the front, so this is negative. Let's simplify what we have. This is, yes, x plus 2y squared z all over y drops downstairs, so this is y cubed plus 2yz. you combine these two fractions, that becomes x over y plus 2yz times y over y. So that becomes x plus 2y squared z over y divided by y squared plus 2z, which becomes the y times your denominator. So you get y cubed plus the 2yz. And don't forget the negative out in the front. Well, it doesn't matter how they expand it. Didn't need all that space. No sense of wasting it, right? Okay. I'm going home on the morning train. In exercise 33 to 36, this is number 35, differentiate implicitly to find the first partial derivatives of w. Still, same old, same old. So we need the partial of f with respect to x. This is going to be a negative sine xy times the derivative of the inside. And so that's going to be with respect to x. So this is just times y. And then any more x's? No. So you can simplify that as this is negative y times sine of xy. What about the partial of f with respect to y? This is negative sine of xy times the derivative of xy with respect to y. It's just times x. Keep on moving. Take the derivative with respect to y. So this is cosine yz times the derivative of yz with respect to y. That's just z. And you can simplify that. This partial of f with respect to y is negative x sine xy plus z times cosine of yz. Then the partial of f with respect to z. This is cosine yz times the derivative of yz with respect to z. That's just y. So this is y times cosine yz plus the derivative of wz with respect to z. That's just w. And then the partial of f with respect to w. It's just z. So now you want to find the partial of w with respect to x, which is by the formula negative capital F sub x over capital F sub w. So here we have this negative times that negative is positive. This is y sine of x, y all over F sub w. That's z. Partial of w with respect to y. Get out of there. So this is negative F sub y over F sub w. This is negative F sub y. It's this long expression here. So you got that negative sitting out in front. You got that negative there. So you can run that negative through if you want to. Let me just put in parentheses right now, and then we'll clean this up afterwards. Negative x sine of x, y plus z of cosine yz. And that's all over F sub w. And that's z. So we clean that up. So the partial of w with respect to y would be x times sine of x, y, minus z times cosine of yz all over z. Now, let's see here. We need the partial of w with respect to z. So this is negative the partial of f with respect to z all over the partial of f with respect to w. So the partial of f with respect to z, that came out to be that this guy right here. So this is negative y cosine of yz plus w, and that's all over z. And that's just good, just the way it is. I guess I could try to make that cosine look a little bit more presentable. Probably not. I think that'll do it. Thank you. Oh, 41 minutes. Sorry.